In this video, we're going to begin our exploration of organic chemistry. We're going to begin by looking at the simplest organic molecules, known as hydrocarbons. Hydrocarbons contain only carbon and hydrogen atoms. Carbon is so versatile because it has 4 valence electrons, which can then achieve an octet by forming 4 different covalent bonds. These 4 bonds can then be bonded to other carbon atoms, hydrogen atoms, or nonmetals such as nitrogen, oxygen, sulfur, and so on. This makes carbon an incredibly versatile atom and is the backbone of all of organic chemistry, making it all of the backbone of life as well. As stated, hydrocarbons, the simplest organic molecule, are made up only of carbon and hydrogen. The octet rule will always apply, so carbon will always form 4 bonds. It can form either 4 single bonds, a double bond and 2 single bonds, a triple bond and 1 single bond, or, less common but still occurring, 2 double bonds. Hydrocarbons are divided up into 4 different classes of molecules: alkanes, alkenes, alkynes, and aromatic. Alkanes will contain only all single bonds, including our cycloalkanes, in which the carbons will form a ring structure. An alkene contains 1 or more double bond. Alkynes contain 1 or more triple bonds. And aromatic hydrocarbons have a unique structure, in this case of a 6-carbon ring with 3 double bonds alternating with single bonds. Note that there are other types of aromatic hydrocarbons as well. However, we will not be discussing those for the purposes of this course. A saturated hydrocarbon is one that contains the maximum number of hydrogens for the number of carbon atoms it has. The formula for a saturated hydrocarbon is C subscript N, which stands for just the number of carbon atoms that we have, and then hydrogen, 2N plus 2. In other words, take the number of carbon atoms that we have, multiply by 2, and add 2, and that will be the formula of a saturated hydrocarbon. For example, if we have a compound with 4 carbon atoms, C4, 2 times 4 is 8, plus 2 is 10. So the saturated hydrocarbon made of 4 carbon atoms will have a formula of C4H10. If we have a formula, perhaps C3H6, we can see that 2 times 3 plus 2 does not equal 6, which simply tells us that this is a molecule that could exist, but it is not a saturated hydrocarbon. It would be either an alkene, an alkyne, or an aromatic, which are all examples of unsaturated hydrocarbons because they will contain fewer than the maximum number of hydrogens for the number of carbon atoms. As a result of carbon's ability to bond up to 4 other carbon atoms, we can find both what we call straight chain alkanes, in which the carbons are all connected in one unbroken line, with hydrogens along the outsides in order to form the octets, or we can have what we call a branched-chain alkane, in which we still have a main chain in the middle. However, we have other smaller carbon chains branching off from that main chain. Those are referred to as branched-chain hydrocarbons. One of the most important parts of learning organic chemistry is learning how we name compounds. Every organic compound has a name based on rules which are developed by the International Union of Pure and Applied Chemistry, or IUPAC. These are quite often referred to as the IUPAC rules. There are 3 basic parts to every name under IUPAC rules: the prefix, the root, and the ending. All of the different organic compounds that we look at naming in this course will follow that same basic structure. Here we see some examples of straight-chain alkanes with their names up to 10 carbons long. What we see here is that the number of carbons will give us the root of every name. If we have 1 carbon, the root is meth. 2 carbons, the root is F. 3 carbons, prop, and so on. And so that number of carbons provides for us the root of all different organic naming. We also see here that the end of all of these compounds is ane, or ane. That is the suffix. The suffix tells you what type of functional group the compound belongs to. All of these are just straight-chain alkanes, and so they will get the suffix ane. Since these compounds are just all straight chains and not branched, they don't have any sort of prefix. We will be discussing prefixes in a few minutes. We have several different ways of writing the structure of hydrocarbons and organic compounds in general. We've discussed Lewis structures in this course already, and here we can see the Lewis structure of pentane. 5 carbons long, so it gets the root pent, and it's an alkane, so it gets the ending ane, and so this is pentane, and the Lewis structure for that. We can also write what we call a condensed structure, in which we don't actually see the bonds like we do in a Lewis structure. We simply write out all of the different atoms. We see first our CH3 group here in the Lewis structure, and CH3 in the condensed structure. That CH3 is followed by a CH2, another CH2, one more CH2, and finally the end with another CH3. We can also write an abbreviation for our condensed structure. Since we have 3 identical CH2 groups in the center of our molecule, we can abbreviate that with CH2 in parentheses and a subscript 3 indicating there are 3 of those. Again, with our CH3 groups bookending it on either side. We will also very often use line structures to represent our molecules. Since carbon and hydrogen are ubiquitous in organic chemistry, it becomes kind of a nuisance to write them in all the time when we're writing structures. And so a line structure does not actually write in any carbon or hydrogens which are attached to carbons. In a line structure, every point or vertex represents a carbon atom. The hydrogens are then assumed to be there in order to complete the octets. In other words, we were just looking at pentane on the last slide, and here's the Lewis structure of pentane. If we're drawing the line structure of pentane, we're going to draw our carbons as points or vertices. And so when we first touch our pencil to our paper, that point is our first carbon atom. We draw up to our second carbon atom, and then we continue in the zigzag shape until we've drawn all 5. 3, 4 carbon atoms, 5 carbon atoms. And so again, each carbon atom is represented by a vertex. This carbon atom here is represented as this point, and so on. This carbon atom is right here. This carbon atom here. This carbon atom is here, and then finally our terminal carbon atom here can be found at our last point. So all those points are our 5 carbon atoms, and then hydrogens are assumed to be there in order to complete our octets. For instance, here at this point, this carbon atom, we can see it only has one other bond in our line structure, bonded to this carbon here. So since there's only one other bond, there must be 3 hydrogens here in order for this carbon to form its octet. And those are these 3 hydrogens in our Lewis structure. Similarly, this carbon is bonded to 2 other carbons. Therefore, there must be 2 hydrogens that are not drawn in there in order for carbon to form its octet, and so on. Here we see a couple other examples of Lewis structures in order to form our line structure, sometimes also called skeletal structures. In our first example, propane, C3H8, we see 3 carbons in our Lewis structure, which makes sense because prop is our root for 3 carbons. And in our line structure, we have 1, 2, 3 carbons. Octane, C8H18, has 8 carbons. Oct is our root for 8. And in fact, we see 1, 2, 3, 4, 5, 6, 7, 8 carbons in our skeletal structure. Cycloalkanes are alkanes which are joined in such a way that the carbons will form a ring. And so the last carbon in the structure will actually be bonded to the first carbon. And so we see several examples of those here. Cyclopropane, 3 carbons in a ring. Cyclobutane, 4 carbons. Cyclopentane with 5, and so on. Isomers are compounds which have the same exact chemical formula, but the atoms will be connected differently, and so they will have different names. We will be talking about naming in just a bit. But for example, if we have the formula C5H12, those atoms can come together in 3 different ways in order to make 3 different compounds. You can see in each case we have 1, 2, 3, 4, 5 carbon atoms. 1, 2, 3, 4, 5. 1, 2, 3, 4, and 5. And if you count up the hydrogens, you will see that in each case there are also 12. There must be 3 here, plus 2, plus 2, plus 2, plus 3 to make 12 hydrogens in this pentane. In this molecule, we have 3 hydrogens here, plus 2, plus 1 on this carbon, plus 3 here, plus 3 here, again for our total of 12. And in this compound, we have 3 hydrogens on this carbon, 3 on this carbon, 3 on this carbon, and 3 on this carbon for our total of 12. Note that this central carbon does not have any hydrogens on it because it already has 4 bonds. Likewise, we have 5 different ways that C6H14 could come together. Again, all the same chemical formula, but the atoms are connected in different ways, making these isomers. An alkene is a compound which will contain 1 or more carbon-carbon double bond, such as we can see right here. Carbon double bonded to a carbon. And so now this carbon has 2 bonds, meaning we only need 2 hydrogens on each carbon in order to form the octet. An alkene with 2 double bonds would be referred to as a diene, and an alkene with numerous double bonds is referred to as a polyene. And we can see an example of that here. Beta-carotene, which is a source of vitamin A, has a fairly extensive structure, and we can see that it has numerous double bonds throughout the entire molecule. So it would be an example of a polyene. As opposed to single bonds, double bonds cannot freely rotate around each other. And so when we have 2 different atoms or groups on the carbon on either side of the double bond, they could be arranged in 2 different ways. As we see here, in each case we have the same chemical formula. We have each carbon connected to 2 hydrogens, then connected to 2 different large groups. If we draw a plane down the middle of our double bond in each case, we can see that in our first one, those 2 big groups are on the same side of the double bond, as opposed to in the second one, those 2 main groups are on opposite sides of the double bond. And so these are what we refer to as geometric isomers. They have the same formula, and all of the atoms are connected in the same way, but there are different arrangements due to the fact that that double bond cannot rotate. When we get into naming compounds, we will see that in these cases, if both of our groups are on the same side, we refer to that as a cis compound. When the groups are on opposite sides of the double bond, that's referred to as a trans compound. And finally, alkynes contain 1 or more carbon-carbon triple bond. Due to the VSEPR arrangement of electrons, alkynes will always have a linear shape around the carbon atoms of that triple bond. Here we see an example of ethyne, F because we have 2 carbons, -ine because that is our suffix for a triple bond. The common name of ethyne is acetylene, and so this is the compound used in oxyacetylene torches. We've talked about how we name straight-chain hydrocarbons, where we simply take the root based on our number of carbon atoms and add the appropriate suffix based on if the compound is an alkane, alkene, or alkyne. We're now going to discuss how we'll name branched-chain hydrocarbons. Normally, in a straight chain, we would have all hydrogen atoms coming off of our carbon backbone. However, in branched-chain hydrocarbons, we will have something for a different carbon group coming off 1 or more of those spots. Here, our naming will remain the same in that we're going to name the compound with our root based on the number of carbon atoms, but now we need to look for the longest continual carbon chain, the longest chain made up of only carbon atoms. And we will refer to that as the parent chain. That is what we will base our name on with the number of carbon atoms. We will then look into adding prefixes before the root in order to tell us what type of substituent is branching off the carbon, as well as where that substituent is located on the parent chain. So again, just as a refresher, we see here our root and suffix for the number of carbon atoms up to 10. If we have 2 carbon atoms, that's ethane, and we can see our skeletal structure here. All the way up to decane with 10 carbon atoms, and we see the skeletal structure of decane right here. So these are all straight chain hydrocarbons, but these straight chains will form a parent chain for our branched hydrocarbons. So let's look at this example. Here we can see we have 1, 2, 3, 4 carbons constituting our longest continual carbon chain. However, instead of two hydrogens on this carbon, we have one hydrogen here, but we branch off to another carbon group. And so when we're naming these branched chain hydrocarbons, the same basic rules apply in that we're going to look for the length of our longest carbon chain, 1, 2, 3, 4. And so our root is going to be bute. This is an alkane with all single bonds, and so we're going to have our suffix ane. But now we need to describe what the actual substituent is coming off of our main chain. When we name substituents, we also use the same basic rules in that we look at our number of carbon atoms. We have one carbon atom in our branch, and so the beginning of our name for our substituent here is going to be meth, as that is our name for one carbon. But when we're naming a substituent, we add the suffix YL. So substituents get a suffix YL. And so the name of this substituent is methyl. And that forms our prefix for the name. We also have to describe where that methyl is coming off of our main chain. When we look at our carbon skeleton, our parent chain, we can see that we have 1, 2, 3, 4 carbon atoms. And if we number those, we can see that our methyl substituent is coming off of our second carbon atom. Therefore, we add a 2 dash in front of methyl, telling us that that methyl group is coming off our second carbon. For our final full name, 2-methylbutane. This guide here gives us our rules for naming our branched chain hydrocarbons. So again, we first locate and assign our root for the main chain, which will be based on our longest continual carbon chain. Don't get confused and think that that must always go straight across. Depending on how the structure is written, sometimes our longest continual chain may go up or down. Again, it all depends on how the molecule is written. If there is a carbon-carbon double or triple bond in the molecule, then we are going to select our longest continual chain that contains both atoms of the double or triple bond, even if there is a longer chain somewhere in the molecule. In the case of alkenes and alkynes, our longest chain will be the one that contains our double or triple bond for our parent chain. If the molecule has two possible main chains with the same number of carbon atoms, then we're going to choose the chain with the greater number of substituents as the main chain. Next, we need to name each substituent. And so again, substituents are named the same way as parents, where we'll look for a number of carbon atoms, but then we will add a YL suffix. We then need to assign a locator number to each substituent, and then assemble the prefix. We will use a multiplier such as di or tri if the substituent appears more than once. For instance, in this example here, we see that we have 2 methyl groups coming off of our second carbon. And so we will have the name dimethyl due to the fact that there are 2 of those methyl groups coming off of our hexane main chain. When we're numbering, we would have to number this 2, 2 to illustrate that both of those methyl groups are coming off of the second carbon. If we're naming substituted alkenes or alkynes, it's a very similar process. We will assign our longest continual chain that contains both atoms of the double-triple bond. Our suffix will now have -ine or -ine. We will number our parent chain from the end closest to the multiple bond. We will then assign any locator numbers to the substituents and add cis or trans, if appropriate, to the front of the name. We also must identify where the double bond is in the molecule. One of the most common ways to do that is to have the number of the carbon atom that the bond appears after before the -ene or -ine ending. For example, if we have this molecule here with a double bond here in the middle, then we would name this according to our general rules of 1, 2, 3, 4 carbon atoms. So bute. The double bond is coming after our second carbon. And therefore, rather than simply calling this compound butene, we would call it but-2-ene to specify where the double bond is located. As opposed to this compound, in which our double bond comes after the first carbon, therefore it would be named but-1-ene. And here we see another example. So in this example, we have our 1, 2, 3, 4 carbon atoms. Note that when we're assigning our main chain, this chain actually consists of 5. However, this chain does not contain our double bond, and therefore our naming of our parent chain must include these 4 atoms, as these include our double bond. And so this becomes our main chain. 1, 2, 3, 4 carbons long, therefore bute. It's an alkene, so we get our ending ene. In this convention, rather than putting the 1 where our double bond appears in between, we're putting our 1 in front. You might see either way. Either way to write this would be correct, either 1-butene or but-1-ene. Personally, I find but-1-ene a little bit clearer, especially as we start to add more and more substituents onto molecules. But either way would be correct. We then need to name our substituent. We can see our substituent here, consisting of 1, 2 carbons, meaning it's an ethyl substituent. It's coming off the second carbon in our main chain, and so 2-ethyl, giving us an entire final name of 2-ethyl 1-butene. Let's look at several examples. In this first example, again, we will use our rules of naming and be very systematic in our approach. Let's first identify our main chain. We have 1, 2, 3, 4, 5, 6, 7 carbons in this chain. 1, 2, 3, 4, 5, 6, if we count down here. 1, 2, 3, 4, 5, 6, if we go that way. Therefore, our longest main chain is going to be this chain right here with our 7 carbons. And so that chain will get the root hept. This is an alkane with all single bonds, and so we get the suffix ane. We now need to name our substituent. Our substituent is right here. It consists of 1, 2 carbons. Therefore, it is an ethyl substituent. And we can see that it's coming off the 1, 2, 3, 4th carbon. Note that it is the 4th carbon from either direction. If we started from the right-hand side, 1, 2, 3, 4. And so either direction gives us a 4 for our substituent. If that were different, You always go with the starting from the side, which gives you your lowest numbers for your substituents. And so here we have 4-ethyl, giving us a final name for this compound of 4-ethyl heptane. Next, we move to this molecule. 1, 2, 3, 4, 5, 6, 7, 8 carbons in that chain. 1, 2, 3, 4, 5 in this one. 1, 2, 3, 4, 5, 6 here. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6. And so our longest chain in this compound is again the one that just goes straight left to right with 8 carbons. And so our root for this is going to be oct. And it is another alkane, and so our suffix will be ane. And so now we need to look towards our substituents. We have a substituent here consisting of 1 carbon. So that's a methyl substituent. Substituent here consisting of 2 carbons. So that's an ethyl substituent. And then we need to look at our numbering. We can see that if we start from the left, we have 1, 2, 3, 4, 5, 6, 7, and 8. Whereas if we start our numbering from the right, we have 1, 2, 3, 4, 5, 6, 7, 8. And so if our numbering starts from the left, we have substituents at 4 and 5. If our numbering starts from the right, we also have substituents at 4 and 5. This would leave us with 2 options. We would either have 4-ethyl, 5-methyl, or 4-methyl, 5-ethyl. We will always write our substituents in the alphabetical order. And so we will always write ethyl before methyl. And so in this case, we're going to choose our numbering from left to right, as that also gives us a lower number for ethyl than it does for methyl, which is written first. And so we will end up with a final name of 4-ethyl, 5-methyl octane. In our next example, we can see that our main chain consists of 1, 2, 3, 4, 5, 6 carbons. And so it will receive the root hex. Again, it is an alkane, so we'll receive the suffix ane. When we look at our substituents, we see that we have 2 methyl substituents coming off of the same carbon. And so we know this is going to be a dimethyl, but now we need to identify which carbon those substituents are on. So again, if we look at our numbering from left to right, we get 1, 2, 3, 4, 5, 6. Whereas if we number from right to left, then we end up with 1, 2, 3, 4, 5, 6. And so we can see that numbering right to left actually gives us a lower number, as that puts our dimethyl on our 3rd carbon, as opposed to our 4th carbon if we number from left to right. And so in this case, we're going to go with the numbering from right to left. And we also need to identify that both of those methyl groups are coming off of that 3rd carbon. And so we will end up with a final name in this case of 3,3-dimethyl hexane. Now let's look at a few examples of alkenes. We can see in our first one that our main chain consists of 1, 2, 3, 4, 5 carbons. Therefore, we're going to have pent as our main chain. We also know that since this is an alkene, our ending is going to be ENE. We can see that our double bond comes after our first carbon, and so therefore it is going to be pent 1-ene. It would also be acceptable to name this one simply 1-pentene. In our last two examples, we're going to see that we have the same number of carbons in our main chain. In this one, we have 1, 2, 3, 4, 5 carbons in our main chain that contains our double bond. In this one, we have 1, 2, 3, 4, 5 carbons in our main chain that contains our double bond. And in each case, we have the same two groups coming off after the double bond. And so the basic name of each of these is going to be the same, but the difference is going to be a cis or trans arrangement. And so let's look at the main naming to begin with. Again, in each case, we have 5 carbons in our main chain, and so it's going to be pent. In each case, our double bond appears after the second carbon, so we'll have pent 2-ene. And then in each case, we also have a methyl group, which is attached to our third carbon. And so our substituent is going to be named 3-methyl. But now let's look at our cis-trans arrangement for each one. So again, if we look down the plane of our double bond, we can see that in our first one, remembering, of course, that there is a hydrogen here, which just isn't written in. And so if we look at our double bond, first, let's explore this carbon, and we look for which group is bigger. We have a methyl group or a hydrogen attached to it. And so it's pretty obvious that our methyl group is the more important group attached to this carbon. However, over here, we can see that we've got a methyl group and an ethyl group attached to this carbon. The ethyl group is larger and therefore would be a, quote, more important group. As opposed to in this compound, once again, remembering that there is a hydrogen written here, which we just don't see. If we look at our first carbon, it looks the same as the other molecule, where our more important group is our methyl above the double bond. On our second carbon, we now have the ethyl above the double bond and the methyl below. Therefore, our ethyl being more important, and we can see that our more important structures are on the same side of the double bond in this molecule, as opposed to the opposite side of the double bond in this molecule. When our more important groups are on opposite sides, we call that trans. When our more important groups are on the same side, we call that cis. And so each molecule will have the same basic name of 3-methyl pent 2-ene. However, this would be trans 3-methyl pent 2-ene, as opposed to this compound, which will be cis 3-methyl pent 2-ene. Comes after. Here are several more examples for you to try. At this point, stop the video, name all of these compounds. When you are confident that you have them named, restart the video, and you will see the names come up for you to be able to check. Remember all the rules that we have talked about. Locate your longest continual main chain, Base your name on that. That will form your root. Then start looking at naming your substituents and where they are located. So try these, stop the video, try these compounds, and then check your answers. Here are all of the answers to those compounds. If you did not get some right, look at the answers and try to figure out where you went wrong. Note that for our double bonds, the names that are showing up for these are Z and E as opposed to cis and trans. It's just a different type of naming convention which goes beyond the purview of this course. But for our purposes, Z will be the same as a cis compound, whereas E will be the same as a trans compound. So look at your answers, try to see where you went wrong for any that are incorrect. And if you are still having trouble with naming, be sure to come see me or check out some of the other resources. I hope this video on hydrocarbons was helpful.